that we have discussed, and we have solved one problem also of infinite line charge. Okay, so we shall continue from there. So we shall take one more problem and we'll come back to the concepts again. So you are given a point charge. Okay, point charge of 200 pi epsilon naught, and this is at 3 minus 1 2, and you are given one more line charge of 40 pi epsilon naught coulombs per meter. It is on x axis, and you have got one more surface charge of 8 epsilon naught coulomb per meter square on x is equal to -3 plane. Okay, you are supposed to find potential at point P, which is at 567. Also, if V is equal to 0 at Q 0, 0, 1, that means the reference voltage is not at the origin. That means reference voltage is not at the infinity, so it is other than infinity. So until now we have seen that the reference voltage was assumed to be at the infinity point. Here there is a small change. That means the reference voltage is assumed to be at point 0, 0, 1. So this is given to you. So you are supposed to find potential at P. That means what is that you are going to calculate here? You are supposed to find Vp due to point charge. You are supposed to find Vp due to infinite line charge, and you are supposed to find Vp due to infinite sheet of charge. Okay, you just add all these things, you will get total Vp here. Okay, so this is the problem, and you are expected to calculate the potential due to each of the charges, that is point charge, line charge, as well as surface charge. Also, the condition is that you have to assume that the reference voltage is not at the infinity but at point 0, 0, 1. Okay, yes. So if the problem is of clarity, please type 0 on the chat box. We will solve the problem. Yes, so these are the values are given to you. Okay, and this is the locations are given to you. So let us write the uh, depiction. So you're having the coordinates like this. Okay, and this is negative x-axis. This is z, y, x. Let me write the point charge first. The point charge is at 3, minus 1, 2. So let the point be here. So this is a point charge. Okay, so let me take it as uh, Q1 here, or Q point, I'll treat as QP, point charge. Okay, the coordinates are 3, -1, 2. Okay, next, let me plot the line charge. The line charge is on the x-axis, that is infinitely long x-axis. So this is your line charge, infinite line charge. So what is the coordinate of line charge? Can somebody tell me? Which is lying on x-axis. So what is the coordinates of infinite line charge? Yes. Line charge is on x-axis. How do you write the coordinates of this one?
X comma 0 0.
Exactly, it is x comma 0 comma 0. So there is no variations in y and z. So there is variations along x only because it is lying on x comma 0 comma 0. Yes. Now line charge is over. Let me illustrate the surface charge. The surface charge is assumed to be on a plane, that is x is equal to -3, that is constant x plane, and it is like this. For example, I will take the plane like this. So this is my plane, so which is at a distance of uh, this length. This length is -3. Okay, so this is my plane, and this is my surface charge, and which is at a distance of minus, that is x equal to -3, and this is on YZ plane. This is on YZ plane. Charges are like this on this plane. Okay. Yes. Now I want to find potential at point P. That point P is on 5, 6, 7. So let me designate the point P here, somewhere here in the space, that is P 5, 6, 7. So this is your point P. So I just have to find out the potential due to point charge at P, potential due to line charge at P, potential due to surface charge at P. Add all those things, you will be getting the solution. Okay. So if this illustration is okay for you, please type 0 on the chat box quickly. Yes. So let me start solving for the potential due to point charge. Potential first, potential due to point charge, potential due to line charge, potential due to surface charge. Okay. Yes. So let me take the first one, potential due to the point charge. Potential due to point charge. So this is my coordinates, and this is my QP, and this is P, and I have a reference point. The reference point is somewhere here, 0, 0, 1, that I can denote it directly on the z-axis. Okay, so the reference point is 0, 0, 1. So this is your reference point, and this is my P. Okay, 0 comma 0 comma 1, and P point is 3, sorry, 5, 6, 7, and point charge point is 3 minus 1, 2. So I require to find the potential at point P. The equation is QP divided by 4 pi epsilon naught RP, okay, or RP Q1, I can write like this, okay, plus C1. So I'll treat this as instead of QP, I'll take this as Q1 so that you'll understand it better. Yes, yes. Now C1 is the constant I'm required to find out, because this is the equation when the reference is not at infinity. So you're supposed to find the equation. Okay. Yes, this is exactly the equation. So let me solve for RPQ1 here. It is nothing but distance, simple distance. So it is a 5 minus 3 square and 6 minus of minus 1 square plus 7 minus 2 square, that is equal to around 78, root 78. So this one I have found out. So that is RPQ1. Okay. So I want to find the C1. Yes, that's the next one to find C1. So let me have the equation like this. V reference is equal to, it is nothing but Q1 divided by 4 pi epsilon naught R. Um, it is nothing but reference to R, reference to Q1, reference point to Q1 plus C1. So I will just take this equation. I'll just leave this slide for a few seconds. Please check out if you got any doubts. Okay. Yes. I will just take this equation onto the next slide. Yes. So V reference is 0. Q1 we got to know it as 200 pi epsilon naught, 4 pi epsilon naught, and R is distance between reference point and Q1 plus C1. R reference point to Q1 is square root of uh, 0 minus 3 square plus 0 minus minus 1 square plus 1 minus 2 square. So this is nothing but root 11. Okay. Now if you solve, if you just substitute this one in the above equation, you will be solving for the constant. That constant turns out to be minus 15.07. So this is the constant to be evaluated because your reference is not at the infinity. Okay. Instead, it is at 0 comma 0 comma 1. Okay. Yes. Now take the original equation. The original equation is this one. let me take that original equation to solve for VP. Okay, so let me take this equation. Yes, now VP is equal to 200 pi epsilon naught divided by 4 pi epsilon naught, and RPQ1 we have solved and C1 we have solved. So RPQ1 was supposed to be 78, root 78, and C1 was found to be minus 15.07. Substitute the values, you will get the answer at, or potential at P as minus 9.41 volts. Yep. So if this step-by-step procedure to find out potential due to a point charge is okay for you, please type 0 on the chat box quickly. Yes. Now we shall move on to the next part, that is potential at P due to line charge, infinite line charge. Let me take the illustration. So the line charge is on the x-axis and point P is somewhere here. This is Z, this is Y, and this is X. Okay, so the point P is at 5, 6, 7. Okay, and line charge coordinates are x comma 0 comma 0, and the reference point coordinates are 0 comma 0 comma 1. So I am interested in finding the potential at P due to the line charge. So VPQ. So I have got an expression for potential difference between 2 points in an electric field due to an infinite line charge. I repeat, I have got an expression for potential difference between 2 points in an electric field due to an infinite line charge that we have discussed in the last class. So that is nothing but rho L by 2 pi epsilon naught logarithm of Rp divided by uh, Rq, sorry, this is Rq divided by Rp. So this is the expression for potential difference between 2 points, that is P as well as Q. Okay, and using this we can solve for VPQ. So how to solve VP? So VPQ is equal to VP minus VQ, and if you take this Q as a reference point, then your VPQ is equal to VP because the reference voltage is 0. Okay, so now I have got 2 points here. This is point Q and this is point P. I can solve VPQ here using this relationship, and from that I can solve for VP. Clear? Is this illustration clear? If it is clear, please type 0 on the chat box quickly. Yes. So let me solve for VPQ using the relationship. For using the relationship, I need to find RQ as well as RP. Okay. Yes, I will just take this expression on to the next slide. Yes. So to find now to find RQ. How to find this RQ? That's the next question. So RQ is nothing but the distance between Q as well as the line charge. Am I right here? The distance between the Q as well as the charge. So the line charge coordinates are x 0, 0, and Q coordinates are 0, 0, 1. So using that, I can find the RQ. So RQ is equal to square root of 0 minus 0 square plus 1 minus 0 square. RQ, Q coordinates are 0, 0, 1, and x that is line charge coordinates are x comma 0 comma 0. You just have to leave that x component. That's all. Yeah. So it turns out to be as 1. Next, I need to find RP also. RP is straightforward. So that means I have to find the distance between the line charge as well as the point P. And this is how I have already found out. So it is 5 minus 0 square plus, 6 minus 0 square plus 7 minus 0 square under the root. Okay. So it is 6 minus 0 square plus 7 minus 0 square under the root. It turns out to be root 85. So I got to know our P value as well as our Q value. Substitute here. So you will be solving for VPQ, that is minus 44.42. Okay. So if this deliberation is okay for you, please type 0 on the chat box quickly. Yes. Now I got to know the value of VPQ, that is minus 44.42, and that is equal to VP minus VQ, and that is equal to VP minus 0, that is equal to VP. So you got the value of VP due to the line charge. Yes. Next, the last component is potential at P due to surface charge. Due to what? Surface charge. Okay. So let me have the illustration here. So you are having like this Z, Y, and X. Okay. And having Q here and having P here. Okay. And this is rho S. So I am required to find the potential at P due to the surface charge. And last class we have also seen that VPQ is equal to a line integral. It is Q to P E vector dot dl vector. Okay, so that we have seen, and this is E vector for a surface charge. We already know that is rho s by 2 epsilon naught into ax cap here. In this case, it is ax cap because x is normal to the yz plane. Okay, and here dl vector is nothing but dx into ax cap plus dy into ay cap, dz into az cap in Cartesian coordinates. Now I got e vector and dl vector. Substitute in this equation, and you can solve for the expression. That is VPQ is equal to minus of Q to P. So it is rho s by 2 epsilon naught into ax cap. This multiplied by dx into ax cap, dy into ay cap, dz into az cap. So everything gets cancelled except the Ax cap component because they are perpendicular to each other. So Q to P rho s by 2 epsilon naught dx you read as x. Okay. Yes. So what is the limits on x here? That's the question. So what are the limits on x here? So x in the Q point, x in the P point. What is x in the Q point? Q is on 0, 0, 1. The x on P is on 5, 6, 7. So x is what, 5. On P point, x is on 0, is on Q point. So the limits turns out to be 0 to 5 rho s by 2 epsilon naught dx. Okay. So integral of dx is what? Integral of dx?
X.
Yeah. Substitute, simplify, and apply the limits. You will be getting it as minus 20 volts. And here also same thing. VPQ is equal to VP minus VQ. That is equal to VP minus 0. That is equal to VP. That is equal to minus 20 volts. Okay. So now just add all the quantities here. The next slide. So VP is equal to V due to point charge, V due to line charge, V due to surface charge, all at P. All at P. Add it, you'll get the answer. Minus 9.41 plus minus 44.42 minus 20 turns out to be minus 73.8. That's all. So if this problem is clear, then you can solve any problem with respect to the potentials. Okay, so let me move to the next concept. It is potential gradient. So this is the voltage and this is the radial distance. Okay, and this is small increment in length delta L, and this is AB, and this is delta V. Okay, so your VAB in this case, it is nothing but small change in the voltage, change of potential, that is delta V. Okay, so that is given by minus E dot into E vector into distance vector. So this is what we have discussed in the previous sessions. So line integral between 2 points is nothing but E vector into distance vector, and you just have to find, that means you can find the rate of change of potential with respect to the distance, that is rate of change of potential with respect to the distance, that is delta V by delta L, and you just have to extend the limits as delta L tends to 0. That is nothing but rate of change of potential with respect to the distance. This is called the potential gradient. This is called the potential gradient, and this is the fundamental expression. From that we have seen this one, potential gradient. So how the potential changes with respect to small changes in the length. It is simply the slope of the graph here. So the slope of the graph. So nothing but dV by dl. Okay. So this is one very important concept. because we have seen the gradient of in case of Gauss theorem, Gauss law, divergence of flux density. There we are seeing discuss the gradient, and here also same thing we'll discuss here, gradient. So next is relationship between E vector and V. We have seen relationship between E and D in the concept of Gauss law and Gauss divergence theorem. So here we shall discuss the relationship between E and V. Okay, so let us take some field like this. Okay, that is the field is given by E vector. Okay, that is E vector, and let me take a distance vector like this with delta L, and is making an angle theta with respect to E vector at this point P. So we know that incremental potential delta V is equal to minus E into delta L, that is dot product. So therefore dV delta V is equal to minus E into delta L into cos theta, that is dot product. So delta V by delta L is nothing but change in potential with respect to the distance minus E cos theta. And if you want to find at a point, so you have to extend the limits. So limits delta L tending to 0, delta V by delta L, that is equal to minus E cos theta. So this is the relationship between V and E, and from this we can find where exactly the um, V is maximum, that is the gradient is maximum. This is the gradient value, where exactly the gradient is maximum, and when the gradient becomes maximum. So that is that we have to check out here. And I think this is very simple for you. So this is the expression relationship between V and E here. Okay. So let me take just this equation onto the next slide and discuss more in here. So it is a limit of delta L tending to 0, and it is nothing but delta V by delta L, and that is equal to gradient dV by dL, that is equal to minus E cos theta. So it will be maximum, the gradient, this gradient is maximum when this cos theta is minus 1. Cos theta is minus 1. So cos theta will be minus 1 only when theta is equal to what? 180 degrees. That means your E vector, this is delta L, and this is E vector, your gradient will be maximum only when the delta L and E are at out of phase, that is 180 degree out of phase. That means your distance vector should be opposite in direction to the field vector. Okay, so then only you can say that the gradient is the maximum. Gradient is maximum only when your distance and the change in the distance is opposite to the the field direction. That means delta L must be in the direction opposite to E, opposite to E. So your dV by dl, dV by dl will be maximum. So when the distance is the delta L must be in direction opposite to E, and the maximum value will be equal to what? E, that is the magnitude of the field intensity. Okay. So what you can conclude from this discussion, that is dV by dl maximum value, that is equal to E. The first point you can conclude is that, so the maximum value of the gradient is always equal to E, and the maximum value of the gradient occurs only when the E is in opposite direction to the delta L. Okay, that means the movement of the points should be opposite to the direction of E. So what I will say, I will just write as this E vector minus dV by dl maximum should be having a normal vector which is opposite to the direction of the field. That opposition is given by the negative sign. Okay, so the equation shows that so magnitude of V is given by maximum rate of change of V when the direction of E is normal to the surface, that is in the decreasing potential. Okay, so this is very important concept, and E will be equal to what? That maximum value is nothing but gradient. That is nothing but gradient. So that is gradient of V, that is given by mm, minus gradient of V. Okay, so gradient of scalar is a vector here. So this is scalar, and gradient of scalar is a vector here. This is a vector here. Okay, so this is very important. Why? Because this gradient, with this concept of gradient, you can derive anything um, with respect to the concepts of materials, concepts of insulation, concepts of waves, electromagnetic waves, like that. So you can find the different things. Okay, so this is very important. So you should know E vector is equal to what? Minus gradient of V, and this gradient of V is a vector, not a scalar. And as we have discussed with respect to divergence, we have got the gradient of V in terms of different coordinates. That is in Cartesian coordinates. The gradient of V is given to be dou V by dou X, and dou V by dou Y in Y direction, dou V by dou Z in Z direction. Cylindrical coordinates, the gradient of V is nothing but dou V by dou R, AR cap, dou V by dou phi into 1 by R into along the phi direction, and dou V by dou Z in Z direction. Spherical coordinates, the gradient of V is given by dou V by dou R, AR cap, 1 by R into dou V by dou theta into A theta, plus 1 by R sine theta, dou V by dou phi, A phi. So these things are very important in solving the problems in different coordinates. You just have to remember this one, and this is nothing but conversion of one Cartesian coordinate to cylindrical to that spherical, like that. So if you know any one conversion, that is sufficient, because it is very simple, and that I have conversion I have given through some videos. Just go through once if you can if you are not able to recall those things. Okay. So what are the properties of this gradient? So the gradient gives the maximum rate of change of potential, maximum rate of change of potential it gives, and it gives the direction. It gives the direction of maximum rate of change of um, potential, that is which is related to field. This potential is related to field, so I can get to know the field. Okay, and also it is the gradient will be perpendicular. The gradient is perpendicular direction to the surface, which passes to the point. So when you solve problem, you'll understand these things. So gradient at any point is perpendicular to the surface, okay, which passes through the point. So this is very important. So we shall just see this one while solving this problem. Okay, problems on the gradient. So this completes the gradient concept, and only one concept is left in this one. That is energy density. Energy density. That I will take up in the next session. Okay. So we are left with only the problems on gradient and energy density, and electric dipole is also one left concept. Electric dipole, as per the syllabus, we are left with only these two concepts. You can just finish it off in the next class. Okay. So I'll just stop at this point. If you got any doubts, you can ask me. Else you can exit. And next class, I'll just take tomorrow morning 8:30, and also during the lab hours, that is from 11 o'clock to 12:15 tomorrow. Okay. Yes. If it's okay, you can exit for the next class. Okay.